In the previous module, we looked at the main features of turbine construction and the essential support systems. Now it's time for us to turn our attention to steam turbine operation and control. And we'll begin by looking at the means of adjusting the turbine's speed or turbine output. The principle of turbine control is very simple. If we need to increase the power output of the turbine, we have to pass more steam through the turbine. Conversely, in order to decrease power output, it is necessary to decrease the amount of steam admitted to the turbine. Turbine steam flow is controlled by adjusting the turbine admission valves, or control valves as they are often called. In the most simple arrangement shown here, we have one control valve, which, depending on its setting, allows more or less steam to flow into the turbine from the steam chest. When the turbine's stop valve is open, the steam chest is charged with steam directly from the boiler. In most turbines, multiple control valves are used as shown here. In this particular arrangement, the steam chest is located above the high pressure end of the turbine's shell. We can see here 8 valves, and these are opened in sequence according to the position of the cross arm, which is itself adjusted by the hydraulic control system. These control valves are set in such a manner that only one valve at a time is actually throttling steam, while the others are either fully open or closed, depending on the actual load. The result is that the throttling losses are smaller than in the case where only one large control valve is used. In large machines, say greater than 100 megawatts, it is more common to have 2 steam chests, one above and one below the shell, or located one on either side of the turbine. In this case, multiple control valves are located in each steam chest, with steam lines connecting to the turbine shell at the high pressure end. In most arrangements of this type, a stop valve is fitted at the entrance to each steam chest. During normal operation, the stop valve remains in the wide open position, while the control valves are modulated to adjust steam flow. The actual opening of the control valves is determined by the position of the operating lever, and this in turn is adjusted by the power cylinder of the hydraulic control gear. This schematic shows us a simplified version of a hydraulic control scheme. In this particular arrangement, a mechanical governor is used to sense turbine speed. Other types of governors are also used, as we'll see in a moment. In this configuration, a change of turbine speed causes the centrifugal weights to move. For example, a decrease in speed causes the centrifugal weights to move inwards and lower the pilot valve. This, in turn, allows more high-pressure oil to enter the power cylinder and raise the piston against the compression spring. This movement of the power piston opens the steam control valve and allows more steam to enter the turbine, which causes its speed to increase. Also note, as the power piston rises, the reset lever lifts the pilot valve back into the neutral position again. On large turbines with multiple control valves, a considerable amount of power is required from the power cylinder. In this case, it's usual to employ a double relay type of pilot valve. In this arrangement, we have high-pressure oil above and below the piston. Now, when the position of the governor spindle changes, say for an increase in speed, the pilot valve lifts and allows high-pressure oil to flow into the space above the power piston. At the same time, the pilot valve exposes the space below the piston to the oil drain and returns the oil to the tank. The high-pressure oil above the piston pushes it downward and consequently moves the control valve in the close direction. At the same time, it also moved the reset lever to bring the pilot valve back to neutral position and so prevented further movement of the control valve. Now let's take a closer look at the governor itself. This mechanical type centrifugal governor is driven directly from the turbine shaft through a gear drive. As speed increases, the weights fly outward due to centrifugal force and lift the sleeve against the compression spring. The sleeve itself is connected to the pilot relay, which in turn adjusts the control valve through the hydraulic servo mechanism. We can adjust the set point of the governor by adjusting the compression on the spring. The adjusting nut moves up or down according to rotation of the screw thread. This action can be performed manually at the turbine, or as is more usual, from a remote position by operation of a small motor drive known as the speeder gear. This name derives from the fact that when the turbine generator is not synchronized to the power system, any adjustment of the governor set point will indeed alter the speed of the turbine. However, when the turbine is on load and the generator is synchronized to other machines, any adjustment of the speeder gear produces an imperceptible change in generator speed. Instead, this action causes a change in steam flow through the turbine with a consequent change in generator output. We'll be talking more about characteristics of the governor and its effect on the electric power system in the next module. Another type of governor used on many machines is the hydraulic governor. In this arrangement, a governor pump fitted to the front end of the turbine shaft is designed to be extremely speed sensitive. As the turbine speed changes, so does the oil pressure output from the pump, and this in turn is used to adjust the position of the pilot valve on the power cylinder. As before, a set point adjustment is provided to allow control of the governor setting and consequently the turbine output. On modern machines, it's more common to use an electronic type of speed sensor and an electro-hydraulic governor. In this arrangement, a toothed wheel is fitted to the shaft. An electronic sensor measures the pulse rate produced by the toothed wheel, and from this calculates the turbine speed. The electronic signal is then processed and converted into a mechanical output that then operates the pilot valve in the normal manner. In these governors, the set point and other adjustments are, of course, inputted electronically to the processor. All of these different types of governors still require high-pressure hydraulic oil to actuate the power cylinder and consequently provide movement to the turbine control valves. The same hydraulic oil supply is used to operate the turbine stop valve. One common arrangement is shown here. During normal operation, the pilot valve is open and allows high-pressure oil to enter the space below the piston and hold the stop valve open against the compression of this high-powered spring. In order to close the stop valve, the pilot valve must be moved to the trip position, thereby allowing the high-pressure oil to drain back to the oil tank. As a result of the sudden decrease in oil pressure below the piston, the compression spring slams the valve closed. As we'll see later, operation of the pilot valve, or trip valve as it is known, can be achieved by any one of several alternative means, including a manual trip, a remotely operated solenoid trip, or a trip signal from various protection devices. On reheat turbines, an additional stop valve and control valve are located at the reheat steam entrance to the intermediate cylinder. We can see the arrangement here. The reheat stop valve functions in the same manner as the turbine main stop valve, and in fact its operation is triggered by the same trip mechanism. So in normal operation, this reheat stop valve is retained in the wide open position, similar to the main steam stop valve. If we wish to trip the turbine under any emergency condition, the trip relay is operated and closes both stop valves immediately. If there were no reheat stop valves fitted, then the large amount of steam that is contained in the reheat piping and reheat tubes in the boiler would continue to flow to the reheat turbine for a short period of time and perhaps cause a turbine overspeed. In other words, we would have no control over this relatively large quantity of entrained steam. The reheat stop valve prevents this from happening. Similarly, the reheat intercept valve is fitted to assist in precise control of the turbine. The intercept valve is in fact a control valve that normally remains wide open, allowing all of the turbine control to be carried out by the main steam control valves. However, in the case of a partial load rejection, perhaps due to a transmission line trip, operation of the main steam control valves by governor action may not be sufficient to hold the turbine speed down. Again, this is because of the entrained reheat steam continuing to pass for a few minutes through the intermediate and low pressure turbines. The intercept valve prevents this. It acts in conjunction with the main steam control valves and actually starts to close in anticipation if the turbine speed rises to 2% above normal. A similar problem can occur with entrained steam feeding back into the turbine from extraction lines. To prevent this, positive closing non-return valves are installed and arranged to close when the turbine is tripped. The valves are actuated pneumatically but are controlled by a hydraulic trip relay. So we can see that our hydraulic system does have an extremely important function to fulfill in operating the turbine. The high-pressure oil pump feeds hydraulic oil to control valves, that is, main steam control and reheat intercept valve, emergency stop valves on the main steam and reheat lines, and a trip relay for extraction line non-return valves. Much of the equipment that we have been discussing is contained in the front-end pedestal of the turbine. In fact, this is often called the governor pedestal. In this schematic, we can see the main oil pump driven directly from the turbine shaft, the power cylinder, which operates the control valves, the centrifugal governor and its pilot valve, an intermediate power cylinder between the governor pilot valve and the main power cylinder, the hand wheel for manual operation of the speeder gear, a load limit hand wheel which can be set to restrict the turbine output, and the trip relay which operates the stop valves. We can also see several devices which actuate the trip valve, such as the hand trip, the solenoid trip, and the overspeed trip. Now at this point, let's take a break and then we'll come back and look at a typical turbine startup. For now, please switch off the tape and review this material in your workbook. In this segment, we're going to look at the actions taken by the operator to perform a typical turbine startup. Of course, we all know that there are different arrangements of turbines and control equipment, but the basic requirements for a startup are the same. Even before we think about admitting steam to the turbine, there are a number of very important maneuvers that must be carried out. If the turbine is returning to service after a long outage, then the first thing we must do is to place the unit on turning gear. This entails running a low-pressure oil pump to circulate oil through all of the turbine and generator bearings and starting the hydrogen seal oil system. The turning gear motor can now be started to rotate the shaft at low speed, usually about 10 RPM. The procedure for charging the generator with hydrogen is detailed in the next module in this series. This maneuver takes several hours to complete, so it is clearly necessary to get an early start and plan the complete operation when returning a unit to service. During a short shutdown, say overnight or even for a few days, it is normal to leave the generator rotating on the turning gear and to keep the generator charged with hydrogen. Of course, if the generator is air-cooled, then we would not be faced with hydrogen charging. However, there is another more vital reason for keeping the unit turning over when it is taken off load. Remember that the internals of the turbine are extremely hot. If we were to leave the rotor stationary immediately after shutting the machine down, experience shows that as the heat rises to the upper part of the rotor, it causes uneven expansion and distortion like this. This is known as hogging, and in some cases the bend may be so severe that the rotor will not recover its original profile even after cooling. Imagine trying to start this machine when there may be contact between moving and stationary parts of the turbine. To prevent this problem, it is essential that the rotor be placed on turning gear immediately after the unit is taken out of service. This ensures that the heat is evenly spread around the rotor and there is consequently no chance of distortion. It should remain on turning gear for several days at least if a long outage is contemplated. Operation of the turning gear after shutdown is so important that in the case of a failure of the equipment, say a motor failure, then drastic action must be taken. One method adopted on smaller machines is to rotate the shaft by hand, if possible, say 180 degrees every half hour. On older machines, this was sometimes achieved by inserting a bar into the coupling. Thus, the first types of turning gear were often known as barring gear. On larger machines, this is not possible, and the only real solution for a failure of the turning gear is to admit steam once again to the turbine and run it up to speed. Well, that's enough about shutdown. We really want to talk about startup procedures. It's evident that in most cases we'll find the turning gear already in service with lube oil circulation. The generator hydrogen cooling system will also be ready for operation, and we'll be talking more about this in the next module. The next thing we must do is make sure that we have steam at the turbine stop valve and that the stop valve drains are open sufficiently to allow any condensed steam to be discharged from the pipework. We'll be discussing the procedure for charging steam lines in another module. Once the main steam line is charged to full boiler pressure, it is now time to charge the steam chest by opening the turbine stop valve. Most modern stop valves are equipped with an internal bypass, which allows a small flow of steam to enter the steam chest in order to raise the metal temperature at a controlled rate. Of course, the stop valve drains will be retained fully open during this maneuver. Eventually, when the steam chest is fully charged, the stop valve will be opened wide and the stop valve drains throttled in. During this period of time, the circulating water system should be started up and the flow of water established through the condenser. We can also begin to draw a vacuum in the condenser by extracting all of the air. Before beginning this activity, it will be necessary to put the gland steam system into operation to prevent air from entering the turbine at the shaft seals. The vacuum pumps or startup ejector are placed in service, and we can observe the indicated decrease in back pressure from atmospheric, about 30 inches of mercury, down to, say, 2 or 3 inches. Summarizing, then, the following conditions must be established before steam can be admitted to the turbine. Lubrication system in service. Turning gear in service. Generator hydrogen system in service where applicable. Circulating water flowing through the condenser. Gland steam system in service, providing sealing steam. Air removal equipment in service with vacuum established in the condenser. Steam line from the boiler charged and turbine stop valve open to charge the steam chest. Stop valve drains and steam chest drains open to ensure removal of any water, that is, condensate, and all protective devices reset and available. In this condition, one method of admitting steam to the turbine and running it up to speed is to operate the control valves by manual operation of the hydraulic control system. In bringing the turbine up to speed, relatively little steam is required, and it is probable that only one or at the most 2 of the control valves will be open or partially open to control the rate of speed increase. This feature has a particular negative impact. For example, looking at this overhead steam chest, we see that each of the 8 control valves supplies steam to just a small arc of the admission nozzles. Consequently, with only 1 or 2 valves open, there would be a tendency for uneven heating of the turbine block. And this could perhaps lead to distortion and eventual cracking of the metal. Even with the side-mounted steam chest, we still have the same problem. In this arrangement, each of the 4 control valves supplies its particular arc of admission nozzles. So the same problem of heat distortion still exists. This method of control is known as partial arc admission. Of course, when the turbine is on load, more of the valves are opened, thus providing more even heating of the nozzle block. On large turbines, this problem is particularly pronounced, and startup is usually performed in a different manner, that is, by full arc admission. In this case, the stop valve is closed after heating the steam chest. Then the control valves are all opened completely, providing access to the complete 360 degrees of admission nozzles. Steam flow to the turbine is then controlled by throttling at the stop valve. This may be carried out by manual operation on a hand wheel like this, or perhaps remotely from the control room. With this arrangement, the turbine governor takes control by throttling the control valves as the turbine's speed approaches its normal operating level. The stop valve should now be opened wide, and the governor set point can be adjusted so that the control valves raise the speed to the nominal 3,600 RPM or 3,000 RPM, ready for synchronizing. When the generator is synchronized and the turbine is on load, the steam flow into the turbine will be controlled by the control valves according to adjustment of the governor set point. Once the unit is on load, the stop valve drains, steam chest drains, and turbine shell drains can all be closed. How long should this startup operation take? At what rate can we raise the turbine speed during startup? Well, this all depends upon the prior condition. That is, how long the unit has been shut down. In other words, is it hot or cold? When we first admit steam to the turbine, it is rotating on turning gear. As soon as the speed starts to rise above turning gear speed, this device is automatically disengaged. At this point, the operator will shut down the turning gear motor. When the turbine is undergoing a cold start, we must allow sufficient time for the various internal components to be heated by the steam flow and expand as uniformly as possible. As shown by this typical startup chart, it may take several hours to bring the cold unit up to synchronizing speed. The manufacturer normally provides startup charts showing the manner in which speed should be raised for different startup conditions. Make sure that you have a copy of the startup curves for each of your particular turbines. Where the unit is undergoing a hot startup, perhaps after an overnight shutdown, the turbine speed can be raised quite quickly within about 30 minutes. The unit can also be loaded quite quickly. The reason for this is that the turbine metal is already hot, probably around 800 degrees Fahrenheit at the steam inlet. Ideally, we should provide steam to the hot turbine at or above that temperature to prevent cooling and the subsequent reheating. This is not as easy as it sounds. In order to raise the steam temperature, we need to fire the boiler harder. But we cannot do that without having an increase in steam flow from the boiler. Even with all of the superheater drains and all of the reheater drains wide open, it may not be sufficient to provide the desired increase in steam temperature. In units which are installed specifically for two-shift operation, a steam bypass arrangement may be built into the system to permit this increase in steam flow during startup. As we see from this schematic, the bypass system allows us to increase steam flow through the boiler, bypassing the turbine. The excess steam is dumped into the condenser, where it is cooled by the circulating water. Of course, there is a heat loss involved, but we do achieve the objective of providing a hot start and improving the life cycle of the turbine. During the run-up of the turbine, care must be taken to avoid as far as possible the critical speeds. Now, what do we mean by this term, critical speed? Well, this refers to a specific speed at which very high vibration occurs due to natural resonance of the turbine. If the rotor is allowed to run for any length of time, even a few minutes, at a critical speed, the vibration would be great enough to probably shatter blades and perhaps other components. In order to avoid this situation, we must pass as quickly as possible through the critical speeds during the run-up. But what are these critical speeds? Well, as our rotating mass is made up of several rotors, for example, the high-pressure and low-pressure turbine rotors and the generator rotor, we may have several critical speeds. The specific speeds will be indicated by the manufacturer, and in fact, the run-up curve provided will make sure that the rotor is not allowed to dwell at any one of those speeds. If you have an automatic startup on your machine, no doubt the run-up program will ensure that the unit passes through these speeds as rapidly as possible. When the machine is first synchronized, it should be loaded immediately to its established minimum load, usually 5 or even 10% of full load capacity. One reason for this is to make sure that there is sufficient steam flow to keep the low-pressure blades from overheating. At very low steam flow, there exists a real danger of overheating due to friction and consequent damage to the very large LP blades. The speed of the outer periphery of these blades approaches the speed of sound, and this creates tremendous friction even under near vacuum conditions. In fact, some turbines are fitted with exhaust hood sprinklers, which are activated if the hood temperature rises above 180 degrees Fahrenheit. Another more mundane reason for loading to about 10% is to allow all of the automatic control systems to be brought into service and stabilized. Now, at this point, let's take a break to give us time to reflect on our discussion before moving on to look at other operating precautions that must be observed. At this time, then, please switch off the tape and thoroughly review this material in your workbook. We've been looking at the main features of a typical turbine startup and the precautions that must be observed. There are, in fact, many other precautions and observations that must be made during operation as well as during the startup of the unit. One very important area is the prevention of water ingress into the turbine. We have already mentioned the need to prevent carryover of water with the steam from the boiler drum. During startup, a certain amount of condensation of steam will occur as the pipework is warmed from cold. Similarly, when steam first enters the cold turbine, condensation will occur initially. It is essential to remove this water to prevent damage to the turbine blades. For this reason, during startup, great care and attention must be paid to correct operation of drains which are fitted to the main steam line, the turbine stop valve, the steam chest, and the turbine shell. These drains usually discharge into the condenser so that the water can be recovered and recycled back into the system. During startup, all of the turbine and any pipework which is connected to the shell, such as extraction steam piping, is under vacuum. We must be extremely careful that any operation of drains, for example on extraction lines, does not allow air or even worse, water to be sucked into the body of the turbine. A representative example is shown here. In this arrangement, the reheater drains are piped to enter a blowdown tank below the water level. But remember, during startup, the reheater and associated pipework is under vacuum, forming part of the steam path through the turbine. You can see here potential for water from the blowdown tank being drawn backwards into the reheater, and from here along into the turbine shell. To avoid this, the reheater drains would normally be connected to the condenser during the startup period. The connection to the blowdown tank would only be used to drain the horizontal reheater before lighting the boiler. Another possible source of ingress of water during on-load conditions could occur as the result of feed water heater leakage into the steam side shell and consequent entrance of water into the extraction steam lines. To prevent this occurrence, positive closing non-return valves are fitted into the extraction lines. If the water level in the heater rises above a predetermined level, the sensor will operate the trip relay to positively close the check valve. These positive closing check valves also trip closed in the event that the turbine stop valve is tripped closed. They are force closed about 10%, and reverse flow completes the closure. An important feature that must be borne in mind is the effect of temperature upon the turbine internals and associated pipework. When we consider that the temperature of the steam entering the turbine is, say, 900 to 1,000 degrees Fahrenheit, it is apparent that its effect upon the metallic components is to cause a considerable expansion. Now, if all the components were to expand at the same rate, this could be accommodated. But this ideal situation is not easy to achieve. For example, when the steam chest is charged, the inside of the vessel will rapidly reach the temperature of the steam. But because the walls of the chest are made very thick to withstand the high pressure, it may take some time for the outside of the wall to arrive at the same temperature as the inside wall. This is especially so because the outside surface is losing heat to atmosphere, even though it is well insulated. Consequently, there will be a temperature gradient between the inner and outer diameter of the steam chest. The faster we try to heat up the inner surface, the greater this differential will be. So what problem could this cause? Well, the result is that the inner surface tries to expand at a greater rate than the outer surface. This could, after many cycles, lead to cracking on the outer surface. But it does not always work that way. For example, as the inner surface tries to expand, but is restricted by the outer surface, the metal becomes compressed and may well exceed its yield point and become permanently deformed. The consequence of this is that when the steam chest cools down with the turbine offload, the metal does not return to its original state and cracks appear on this inner surface. So it is extremely important when heating steam pipework, the steam chest and the turbine itself, to make sure that we do not try to add heat too quickly. One commonly used rule of thumb states that the temperature rise of metallic components should not be allowed to exceed 500 degrees Fahrenheit per hour, that is 8 degrees Fahrenheit per minute. Another accepted limit states that the temperature differential across the walls of pipework, steam chest, and so on should not exceed 200 degrees Fahrenheit. On most modern turbines, thermocouples are embedded into metal components at various strategic points, such as the steam chest and shell inner and outer surfaces. These temperatures are usually recorded to give the operator guidance during startup. You must make sure to learn and remember the limits which are established for each of your turbines. In order to increase the output of the turbine, steam flow is increased, and this consequently adds more heat to the metallic components, causing expansion. The operator must take care not to increase steam flow or steam temperature too rapidly, as this could lead to unequal expansion of components and possible distortion. When this occurs on the rotor, it leads to an increase in eccentricity. The shaft and rotor take on a slight bow due to temperature distortion, and this is exaggerated by the centrifugal force of rotation. Eccentricity is dangerous because it results in a reduction in radial clearance between the rotating and stationary parts. The degree of eccentricity is measured and recorded at the operator's terminal or control board. In most machines, an eccentricity of 5 mil is considered very high. High eccentricity also shows up as an increase in vibration at the bearings. In actual fact, the expansion of the turbine components in the radial direction is quite small. On the other hand, the longitudinal expansion, that is, in the axial direction, is considerable, perhaps 1 to 2 inches between the cold and full load condition. We have already seen how the turbine construction allows for the shell to expand axially, usually on sliding feet at the governor pedestal. Now, while this is happening, the rotor is expanding, but in the opposite direction. Remember, the high-pressure end of the rotor is secured by the thrust bearing. It would be convenient if both the rotor and the shell were to expand at the same rate. But in practice, this does not happen. The reason is that the rotor is considerably lighter than the shell, and therefore it expands more rapidly. So during the initial loading of a cold machine, the rotor expands at a greater rate, and in fact, we run the risk of the rotating blades coming into contact with the next stage of stationary blades. This differential expansion must be kept within certain limits by restricting the rate of change of load on the machine. Differential expansion is measured and indicated at the operator's control panel or console. Typically, during startup, we will observe a positive differential expansion increasing continuously up to about 100 or 150 mil. We may have to restrict loading in order to keep from exceeding this level. Eventually, as the casing expands further and further, the differential will decrease and probably settle down to, say, plus 50 mil. The reverse situation occurs during a shutdown. In this case, the rotor contracts much more rapidly than the shell, and as a consequence will reduce the differential expansion and generally move into the negative zone. Normally, the manufacturer sets limits of differential expansion for both the negative and positive sides. The expansion position of the governor pedestal is also indicated. After a short overnight shutdown, it is probable that the turbine's shell will still be considerably expanded, while the rotor has contracted to provide a negative differential. This indicates that a hot start is required. Please make sure to check the manufacturer's recommendation for your particular machine. We mentioned just now that bearing vibration can be an indication of various turbine problems. These include excessive change in steam temperature or steam flow to the turbine, high eccentricity, water ingress, internal mechanical defects of the turbine, bearing defects, and a change in alignment of the bearings due to a sinking foundation or other bearing support. The vibration on each of the turbine and generator bearings is continuously monitored and recorded. It is important that the operator keep his eye on these reported levels of vibration. Any sudden change will certainly indicate the occurrence of a potential problem. For example, increased vibration on a generator bearing at a certain loading has been used to identify problems with the generator windings. Similarly, a temporary increase in turbine bearing vibration may be an indication that the operator is applying load too fast. If the magnitude of vibration on all turbine bearings steadily increases with time, it is probably an indication of wear and tear on mechanical components as the machine approaches the next overhaul period, usually every 5 years. In very general terms, the magnitude of bearing vibration should be less than 3 mil. In many machines, an alarm will be enunciated if any bearing vibration exceeds 5 mil. Most of the monitoring equipment we have discussed in this segment forms part of the turbine supervisory equipment. Commonly, this includes the following information: differential expansion, pedestal position, shaft eccentricity, vibration on all bearings, metal temperature at specific locations, turbine speed, percentage opening of control valves, and mechanical position of the shaft. Now, before we move on to talk further about monitoring equipment and turbine protection devices, let's take a break. Please switch off the tape now and review this material in your workbook. The major protective device on the steam turbine is the main steam stop valve. If it becomes necessary to stop the turbine due to an abnormal operating condition, the stop valve must be tripped closed. In the case of a reheat turbine, both the main steam stop valve and the reheat stop valve will be tripped simultaneously. We have already learned that the stop valve is closed by actuation of the pilot relay or trip relay, which drains oil pressure from the hydraulic system. There may be several trip relays located on the hydraulic system, actuated by different protection devices. Operation of any trip relay should cause the following action: closure of main steam stop valve, closure of reheat stop valve, closure of steam admission valves, positive closure of extraction line non-return valves, trip open the generator breaker, trip open the generator field circuit breaker, and activation of alarms and annunciation. So what are these hazardous conditions that are considered severe enough to automatically trip the turbine? Well, the most dangerous condition that must be avoided is that of overspeed. And this could occur in the case of a load rejection, for example. Similarly, we would get the same result if the generator breaker was tripped open by mistake when the unit was loaded to about 50% capacity. Of course, the turbine generator would immediately increase speed because at the instant of the breaker trip, a very large quantity of steam is flowing through the turbine. Under normal circumstances, the governor should be able to close the turbine control valve sufficiently to bring the speed close to normal within a few seconds. However, imagine what would happen if the governor failed to act properly, or the power piston seized, or some other defect prevented movement of the control valves. In this case, steam flow to the turbine would continue, with the result that the speed would rapidly rise to 2 or 3 times normal. In practice, the speed would not get that far because centrifugal force acting on the mechanical parts of the turbine and generator rotor would cause them to break up. Several instances have been reported of turbine blades and sectors of turbine wheels passing right through the turbine shell into the turbine room, with the potential for injury to plant staff and damage to other equipment. In order to prevent this possibility, 1 and sometimes 2 quite separate overspeed protection devices are installed and set to operate at 10% and 12% overspeed. Each protection device operates a trip relay to close the stop valve and other protective action as already discussed. Here we see an example of a traditional mechanical overspeed device. Essentially, it consists of a bolt inserted into the shaft. As the shaft rotates, the bolt tries to fly out by centrifugal force, but this is restrained by a compression spring. The spring is carefully adjusted so that the centrifugal force does overcome the spring compression at 10% overspeed. The bolt then mechanically trips the latch, which allows the trip relay to move to the trip position, so draining off hydraulic oil and closing the stop valve. You will remember that tripping the stop valve also actuates the positive closure of non-return valves on the extraction lines. This is necessary to prevent entrained steam being drawn back into the turbine and aggravating the overspeed condition. Another common type of overspeed relay uses electrical measurement of speed and an electrical circuit to initiate operation of the trip relay through a solenoid. It is vital that these overspeed trips be checked for operation at regular intervals and the actual tripping speed be recorded. Now, this may be done when the unit is being shut down or started up. Adjustment of the setting may have to be made from time to time. This protection device is one of the most important on the turbine. On a condensing turbine, we expect the back pressure in the condenser, and therefore at the turbine exhaust, to be between 1 to 3 inches of mercury, depending upon the actual cooling water system. Now imagine what would happen if the back pressure started to rise, perhaps due to a large air leak into the condenser, or more likely a reduction in cooling water flow through the condenser. Now remember, as the back pressure increases, so does the density of steam at the turbine exhaust. With a back pressure of 10 inches, the density would be about 9 times greater than the density at 1-inch back pressure. This increase in density greatly increases the friction on the LP blading, which is still turning at 3,600 RPM. The result leads to overheating and possible damage to the low-pressure blading. In order to prevent this situation, a vacuum trip continuously monitors the back pressure, and it is usually set to operate a trip relay when the back pressure reaches 10 inches of mercury. The monitor will sound an alarm when the back pressure reaches 5 inches mercury, so as to warn the operator to take action before a trip occurs. While we're talking about back pressure of the turbine exhaust, let's consider what would happen if during a startup we passed steam through the turbine before establishing cooling water flow through the condenser. Well, the steam entering the condenser would not condense and consequently would build up pressure eventually to such a level as to rupture the exhaust hood. In order to prevent such an occurrence, a large relief diaphragm is fitted to the exhaust hood. This is normally held in place simply by the vacuum inside the hood and atmospheric air pressure outside. As soon as the pressure inside the hood rises above atmospheric, the diaphragm opens, acting as a relief valve to prevent any damage to the exhaust hood casing. This diaphragm works quite independently of the mechanical devices and hydraulic mechanism that we have been discussing. Usually, the only attention required is to make sure that the water seal around the edge of the diaphragm is not leaking and allowing air to enter the condenser. Another important protection device that is set to trip the turbine is the thrust-bearing failure monitor. This equipment is fitted to precisely measure the position of the thrust collar in relation to its pedestal. As long as the thrust bearing on either side of the collar is operating correctly, there will be no change in the relative position of the collar, even when the turbine shell and the turbine rotor expand. If the thrust bearing were to fail, allowing axial movement of the rotor, we could run into the serious problem of contact between the rotating and stationary blades. Therefore, it is essential that at the first sign of thrust collar movement indicating failure of the thrust bearing, the trip relay be activated so as to close the stop valve and bring the turbine to a halt. Another condition which will cause the turbine stop valve to trip is loss of lube oil pressure. If lube oil is not available to provide lubrication to an operating machine, the bearings will rapidly overheat and fail, with possible disastrous consequences for other components of the turbine and generator. Lube oil is monitored continuously, and if pressure falls to 0 or a very low value, a trip relay will be actuated to trip the turbine. Note that this relay will also prevent the opening of the turbine stop valve if lube oil circulation has not already been established during startup. In the case of hydraulic oil, an alarm is usually fitted to indicate low pressure. But a trip relay is not always provided. This is because the hydraulic equipment is designed to operate in a fail-safe manner. If the hydraulic oil pressure fails, both the stop valve and control valve will be closed by spring pressure in their respective power cylinders. In addition to the protective devices mentioned, the operator has the option to trip the unit manually by operating the trip lever, which is usually located on the turbine pedestal. On most units, it is necessary for the operator to reset the trip mechanism manually at the turbine pedestal after any trip has occurred. The operator can also trip the unit remotely from the control room. This is simply a remotely operated solenoid which operates the hydraulic trip relay. This solenoid trip may also be activated by certain generator and boiler protection devices. For example, if an internal fault developed inside the generator, it would be necessary to trip the generator breaker and the field switch, and also the turbine stop valve to bring the generator to a stop as soon as possible. Similarly, if a fault on the boiler was serious enough to cause a boiler trip, then the turbine stop valve would also need to be tripped at the same time. Otherwise, we would be pulling steam and possibly water out of a shutdown boiler. Summarizing then, let's list the major protective devices that are installed on most steam turbines: main and reheat stop valves and associated hydraulic trip relays, positive closing non-return valves on extraction steam lines, overspeed trip, low vacuum trip, thrust-bearing failure trip, loss of lube oil pressure trip, manual trip lever on the front pedestal, remote solenoid trip by operator push button, and generator or boiler protection intertripping. It is vital that all protection devices be tested regularly to ensure that they will actually operate when required. In some plants, the turbine generator may remain on load for many months at a time. In this case, some form of simulated test may be carried out. For example, partial operation of the overspeed trip mechanism is actuated, but actual tripping of the turbine is blocked. An extremely important test maneuver is the exercising of the turbine stop valves. The test circuit allows the stop valve to partially close and then open again. This test is performed daily in many plants, and the objective is to make sure that the stop valve does actually move and not remain frozen in the open position, as has actually occurred on some occasions. All of the protection devices in the world would be of no use whatsoever if the stop valve failed to close when commanded. For a similar reason, the positive closing non-return valves on the extraction lines are also exercised daily or at some other regular interval. Make sure that you are thoroughly familiar with the established procedures for testing protective equipment on your turbines. Also, using the information that we have presented here, make sure that you know the function and location of all protective devices on your particular turbines. And note that there are certain items of equipment that could be considered protective, but they do not actually trip the stop valve and shut down the turbine. For example, a low-pressure deloading device is often connected to the hydraulic control valve system. The objective of the deloader is to protect the turbine against falling steam pressure from the boiler. For example, a defect on the boiler auxiliary plant may reduce steam output from the boiler. But as the turbine is not aware of this, it will continue to pull the same steam flow out of the boiler, with the consequence that the pressure falls and will continue to fall as long as this condition prevails. The danger is that with falling pressure, the water level in the boiler drum will rise substantially due to swell, and this in turn may lead to carryover, that is, water passing along with the steam into the turbine. To prevent this possibility, the deloading device monitors the steam pressure. If this falls below 80% of nominal, the deloader starts to close the control valves to maintain the steam pressure at 80%. Of course, this will reduce the output of the turbine generator, but this is far preferable to damaging the turbine. During startup of the unit, which may well take place at low steam pressure, the deloading device is bypassed and only brought into service when the unit is on load and boiler pressure is normal. Most of the turbine operations are performed remotely from the central control room, with the support of regular local inspection by a roving operator. In traditional control rooms, the operator works at a large panel which includes switching controls, indicating lights, indicating instruments, and recording charts for the complete unit, that is, boiler, turbine, generator, and auxiliaries. The annunciator panel, usually located above, provides indication of any alarm conditions. In newer plant installations, and in fact in many converted plants, digital control systems are employed, and in this case, the operator works at a console with 3 or 4 CRTs, providing indications, alarms, and the means for remote operation. Referring to turbine operation, the indications we are most interested in are steam conditions, that is, pressure and temperature, vacuum, usually dependent upon certain water conditions, lube oil temperatures, bearing vibration, and mechanical condition of the turbine as indicated by the supervisory instruments. Now, in this module, we have only been able to cover the most common features of turbine operation. Using this information as a guide, you must make sure to thoroughly learn and become familiar with your own turbines. No doubt each of your machines will have their own idiosyncrasies, which become well known to the experienced operator. Please switch off the tape now and review this material in your workbook.